right, the door has closed, so that's my cue. And it's open again. All right, I'll get started. My name is Wouter Cloetens. I work for SoftAtHome. My boss, Wojtek, has introduced us during the panel this morning already. We make a software stack for routers specifically. I'm the architect of that. For major operators, we do software upgrades in the field. A lot of Cesare's results for France, etc., are due to us. I'm going to be talking to you about containers and virtual machines running inside home routers. Maybe just a shout out, I didn't mention the name, but I stole almost all of these slides from one of our developers who actually implemented the container framework. So even though it only has my name, credit goes to Tom Tierens who wrote this. We do maybe a bit of background. So we do upgraded routers in the field, owned mostly by service operators. The volume is so large, and the concern of our customers with the quality of the routers in the field is so high that they're very careful about the software upgrades. When we do a software upgrade, it goes through internal testing, it goes through field trials, it goes through larger field trials, then it goes to full deployment. There can be anywhere up to from 6 months to a year between us delivering the final build and it actually getting deployed in the field. The main reason for this is just simply fear of regressions. We don't want to introduce any problems for customers with their routers. All the services, voice over IP, IPTV, television, etc., and obviously the internet access have to keep working smoothly. There is really practically no margin for error. Which means that it makes it very difficult to start deploying all sorts of interesting new features and applications to those routers. There is, of course, a lot of interest from the marketing department and the technical departments to say, well, we could offer this and that to our customers, but how do you make sure that you don't cause any regressions? Well, one of the ways would be isolation. And containers and virtual machines are a way of doing that isolation. They're not the only way. If you think that this is a simple solution, by the end of this talk, you will be in tears. Right. So the idea of that would be to actually reduce the Q&A cycle. To clarify it, that if we deploy a virtual machine, or a container inside a box, we don't have to go through all the other testing anymore. We can have shorter cycles for those applications, and we deploy new versions every 3 months or so. We have actually done some deployments in the field. Another piece of information, we're not currently using OpenWrt, but I thought that this would be interesting to share, because at the end of the day, Linux containers are Linux and don't really have anything to do with the rest. So, containers, what are they exactly? The first part is about giving you some background into the actual technology, and I'm going to try to go quickly through that. A container is not the same as a virtual machine. The hardware is not virtualized. It's sharing the same kernel. You can't run it anywhere else than on Linux. You are not completely shielded inside of a container. I'll go more deeply into that. And it doesn't solve all your security problems, mostly due to the fact that you're still sharing the same kernel. So what do you need? So you need a fairly recent Linux kernel over 4.1 for reasons I'll show later would be a good choice. LXC is the Linux container framework. There are also management frameworks on top of that. The logo on the right is of Docker that is very familiar to most of you. The one on the left is LXD, which is kind of like a Linux container hypervisor as the way they market it. They do similar things. We obviously looked first to see, is there anything in open source that can solve our use cases for us? And we came to the conclusion that these things are very much focused towards servers and not so much towards embedded systems, and which led us to design our own solution to give us all the possible freedoms. So yeah, both of those, both Docker and LXD actually use LXC. We'll start with the isolation bit. So you want to deploy a service and you want to make sure that it's isolated from the rest of the system. The basic thing is that, okay, so you have a, why am I not seeing, oops. The colors are missing from this presentation. Right, I'm sorry about that. There's supposed to be a circle here, but one of my colors, blue color, seems to be completely filtered out. If you run a process as root, as one of those processes, you have access to pretty much everything. You're all familiar with that. The first thing you could do is discretionary access control, standard Unix user ID and passwords. You make sure that the files and the sockets, IPC sockets, all other special files, device files, and that sort of thing are not accessible to that user, and you make sure that there's some sort of a separation of what that user can do. You can go more secure than that, and you can use capabilities. You can set capabilities on a process and saying that you're not allowed to call some of the system calls. You can actually go to the next step and say that now we're going to use namespaces. And this is one of the essential parts of containers. The namespaces means that you create kind of a virtual Linux environment for every one of those processes. You can choose any one of those namespaces individually. A network namespace, well, I'll go through them in more detail later, but they isolate you from the rest, such as a network namespace, for example, can make sure that you cannot see all the network interfaces or use all the network interfaces. The PID process namespace will ensure that you don't see any of the other programs running, you just see yourself running. The network's namespace, can present virtual network interfaces. The process namespace can show you, on the right here, you can see that you can only see the processes as if you're running on the dedicated machine, only the processes within your namespace. The mount namespace can ensure that you can have actually visibility over certain file systems or other things is restricted. The user namespace is an interesting thing that would allow you to make sure that if you are root within the container, you're not root outside of the container. That's one of the reasons why you might need a newer kernel. When the IPC namespace ensures that some of the IPC mechanisms are not accessible, you cannot do inter-process communication with systems on what we call the host environment. The UTS namespace, as far as I can tell, all it gives you is that you can change the host name of your system. The next big element of containers is C groups. Those actually make sure that you can restrict the hardware resources that a particular process can use. You can say that, okay, you're only allowed to use so much % of the CPU. You could force it to say that you can only use this CPU. In an SMP system, you could say that, well, the second CPU is dedicated for you, the first CPU for the critical resources. You can do a prioritization of disk I/O and other I/O, for example, as well. And a very interesting thing is that you also have the ability to freeze processes or an entire group of processes and start them up again. At that point in time, you still have access over the entire file system, which you might not want. You might have situations like in your host router environment, you have a host APD configuration file. It has your pre-shared key in plain text inside embedded in it. You don't want just any process that might not be fully trusted or that is facing the network and potentially vulnerable to a network attack, that it can access this file at all. So you can change the root file system. Change root is not perfect. There are ways of breaking out of it, but at least you can get it to seemingly have its own root file system. The next step is mandatory access control. There are a few that are available to really tell the kernel that your process is only allowed to do these things. This is not standard part of containers, but these are things that you can do additionally. We mostly looked at SE Linux, and we did an implementation with AppArmor. Those give you the ability to say that you're allowed to access certain files from this process, and if you try to access anything else, we will report it, or we will kill you, or whatever, or we will deny. The requirements are somewhat similar, although different in how you configure them. A next step is something that is not always usable, that is seccomp, which means that you can really isolate a process so that the only thing that it can do really is computing logic. It cannot open any files, it cannot do anything else than work on its own. There are very few applications where we have that's good for compute tasks, but it's not really there. So at the end of the day, so you have if you do that for a particular process, then you have a completely isolated process, all of those things, or a selection of those things. If you do that for an init script, then you basically have a lightweight virtual machine. You have an init script, and you have all the processes that are started within that are within your little, seemingly a virtual machine. There are the container frameworks. What those give you on top of what you have is, with those standard Linux features, are the ability to start the whole thing, stop the whole thing, do an installation in case of LXC, to do LXD and LXC, and Docker will also give you the ability to do deployments and push those somewhere, remotely manage the containers that they are started and stopped, see how much, what the resource consumption is of them. Can you go more secure? Yes. So at some point in time, you still have the same kernel. You will, and any hardware you need access to, you will need to have a driver in your host environment, and those drivers might not always have the right code quality. You still have the problem that you're sharing the kernel with the host environment. If there's a bug in the host environment, something exploitable, then from inside the container, you could exploit this and attack the host environment. Your accounting of the C groups might not always be perfect. You could incur from within a container a certain load that does something else in the kernel, and it isn't counted as I/O or memory or network operations by that container. So there are some leaks. A stronger isolation, therefore, is that for your environment, you run your own kernel, and the hardware interfaces are fully virtualized. If you want to get to a particular hardware resource, either it's going to have to be in a method where you have dedicated access to that hardware resource, that the system allows you to do that, like a NAS functionality container could, for instance, get dedicated access over the USB host controller, if that's the only thing you're going to be doing with USB. Or you need to virtualize that, so the USB, the SATA, the network interfaces would all have to be virtual drivers that need to be implemented and that somehow need to be able to map to something in the host environment. So in terms of virtualization, and just to be clear, we're not there yet. The hardware capabilities are appearing in some router system on chips, but certainly the software support around that isn't quite there yet. There are some advantages and disadvantages mapped out here in sense of what you can gain from either. It's not really a matter of which is best, it's a matter of which is best for your application. So you certainly, the ability to have different kernels in your virtual machine versus in your host environment gives you freedom to do an upgrade of a kernel in one of them without affecting the other, for example. Gives you the ability to run a non-Linux operating system. I'm going to apologize for number 5 here to Bradley, who should be here as well. The unfriendly open source refers to GPL licenses that make it difficult for us to deploy certain applications with a license that would mandate that the user can change his environment or his software. Maybe if we deploy it in a container or in a virtual machine, we'll be able to give the user that freedom to indeed do that without affecting the essential service that our customers are so worried about. The number 8 here is really a crazy idea in that, well, if you're going to do a certain application deployment in a container or in a virtual machine, maybe you can have a choice as an operator to say that, well, for this particular setup, it would be a good idea if we push it to the edge of our network, to the CPEs in the user's homes, or perhaps we should deploy it in a virtual machine somewhere in the cloud and give him some sort of a dedicated tunnel towards it, depending on the... That sounds simple, and it's certainly not so simple. There is a serious memory overhead incurred by a virtual machine compared to a container. A container is essentially almost free. It runs in the same Linux kernel. If you're going to start up a whole extra Linux kernel, that is going to take really a lot of memory. There are, of course, certain hardware requirements that you have with virtual machines as well to be able to properly do that isolation. So you do not have that problem with containers at all. If you have Linux, you can do containers. Right, so containers are available now and are very efficient. Hardware virtualization can fix some things, and they are coming. The capabilities are coming in the router SoCs. You really have the choice for your application, which one makes the most sense. We expect to be able to keep doing both. Right, how does this refer to embedded platforms? I said so far what the technology was, what you can do with it, is the next chapter. So, okay, so what are you going to do with it? As mentioned, you could isolate a single process or create a lightweight virtual machine. The robustness and the security should be obvious. The isolation was the part. You could allow third-party applications to be deployed on your router without having to worry too much about what the impact of this is. This has hurt us quite a bit in the past in that customers have pushed us, we would really like to deploy this application, and we say that, yep, but then we're going to want to have the source code because we really want to do a full security audit to make sure that this thing is not going to impact our system. If you have a vendor of software that says that, well, I don't want to do that, then game over for us. We really do not want to take that risk. With containers and virtual machines, with that isolation, we could do that. You can look at the slides later. I will share them. I'm going to go quickly over these because I really have a lot of slides. It basically lists the advantages and disadvantages of the various models. One of the things actually you can do with a container as well in a single process is that you can simply use it as a jail for a process. A web server, for instance, would be good that it remains in its own jail, and that could be a Linux container. It doesn't have to be just a change root or just a privilege separation. Okay, now you're going to need to make choices, and this is where it gets nasty. You might think, we've had customers, marketing departments going that, let's just put it in a container. We can just deploy an application, you know, like on the App Store. You can do it with Android and iOS. Why can't you do it with a router? Well, we don't have the gigabytes of flash typically, with some exceptions, people here in the audience. We don't typically have the gigabytes of flash to ship an entire environment with a single application. There are certain efficiencies that we really need to take into account. So your device limitations are a factor of what you're going to do, and you might say that, oh, a virtual machine would be perfect, but I'm sorry, if you have 128 megs of RAM, it's probably not the right choice. This is an overview of the Linux kernel versions that will have the various features that we discussed, all the way from namespaces to seccomp. As you can see, by Linux kernel 4.5, we have the final version where we have the ability to have the actually unprivileged containers not running as root within the container, which might be which is a very important one. Right, so take your pick. You don't need to do everything always. Some of them are fairly easily configured and activated. Some of them are a bit nastier. If you're going to mess with the file system, you're going to have to make some choices. If you're going to apply mandatory access control, you have a whole bunch of configuration to perform, etc. Here's one with the networking. There are a lot of different choices for networking in LXC. The empty networking concept just specifies that you don't need networking at all. The ones that I'm going to start going a bit quicker. The none is that you have access to all the networking environments. VETH gives you a virtual Ethernet interface between your host environment and your container. MacVLAN VPA is the one of the three different options in MacVLAN that we've used at some point in time to just offer something on the LAN side, but then you need to have a different MAC address and IP address on the LAN side. There are also benefits and disadvantages to all of them. Your root file system, you should, let's see what I'm going to skip here. What we have done is actually that we have used a squashfs images if we're going to do a deployment of a container into the box. We can have a container that's already present in the root file system in a subdirectory in its change root, or we can push an image that is cryptographically signed that contains all the configuration for the container plus the root file system itself for the container. I'm going to skip over some of those things. There are alternatives. You can be more efficient. You could, if you're going to have multiple containers, say that you're going to share some sort of a base root file system, which is this one here. You could use overlayfs for that. You could also use hard links from your main file system. Many, many choices that all have their benefits and drawbacks. A RAM disk, you should probably have one. TMPFS is good because it's counted as the memory in C groups as the memory of the container itself. Persistent storage is a difficult one. Where are you going to let your application inside your container keep its data? You really want to separate that. The quota system of Linux really is not suitable. A separate flash volume is an option, but you could also do it in different ways. Finally, a couple of case studies of actual solutions that we have built. One of them is that we have built a NAS environment within a container, which has a separate upgrade cycle than the main router software. So we limit the amount of CPU, RAM it can use. We have given it its own root file system, and it's really like a lightweight virtual machine. We keep a separate flash partition just to store the image. We have created two virtual Ethernet interfaces, one to communicate locally to the host environment and knotted towards the WAN interface, and another that is in the LAN bridge available over the LAN side, with the implication that it has its own MAC address and IP address, so the end user has to be aware that his NAS functionality seems like a separate box. USB storage, this is a kind of a semi-trusted environment. We know what the code is running in the NAS. So the selection of which USB devices are assigned to the host versus those are assigned to the container are simply done with UDEF rules in the container. If it's the storage device, it will grab it. If it's not a storage device, it won't touch it. A second use case is an untrusted third-party application store, and there all the security aspects start coming in. And the basic thing is that we'll have to upgrade the kernel to do that. We'll have to do all sort of fine-grained management, which makes it very difficult because you want to say that, okay, I want third-party developers to have our SDK, deploy an application, and just ship it. Okay, but that means that you're going to have to start making all the different rules and audit everything that it, for AppArmor, for example, and audit everything that it needs to do and choose the right limitations, then it becomes a very difficult vetting process for whoever maintains the App Store to say that they're going to deploy that or not. And in this case, there is an inherent risk here. Hardware virtualization might actually be the better choice. Okay, I think we have 1 or 2 minutes for questions still. See, the lack of coffee and the speed of of me going through 78 slides has lulled you all to sleep, I think.
Question regarding the container format. Have you tried to look at OCI, Open Container Initiative?
Yes, the developer who did the initial analysis has looked at a bunch of evolutions. We started this work first 2 years ago. 1 year ago, there were certainly interesting aspects there. But at the end of the day, we came to the conclusion that any framework that existed was not entirely suited for the embedded environment that we had. It would be good for us to actually check again at this point in time.
Well, practically, like OCI is currently evolving, so you can, if you see what something is missing, you can try to contribute where, like why to create one more.
Yes, indeed. Specifically, the customer who wanted to deploy this last solution, they have also been a big pusher to say that let's do something standard, and if there isn't anything standard, or there is something that's doesn't completely match our requirements, let's start cooperating with them. Because indeed, we really do not, if we take this very far, we don't want to do it on our own. We want to be able to use some sort of a standard framework at some point.
So that's all the time we have for questions. Thank you very much.